Welcome to Ready to Derive. In this video, we're going to learn how to find the volumes of three-dimensional objects by the method of cross-sections. So what might an object look like that would require this method? Well, here's a beautiful photo of a building in which you can see that the triangular cross-sections, roughly triangular cross-sections, are repeated. Those triangular cross sections get larger and larger depending on the width of the floor. And to kind of simplify this image, I've done, here's a little floor plan I have going on. I'm going to just take a triangle, place it at the very end there, and then just keep adding these structures in to kind of create this three-dimensional building. Now, you can see that the cross sections, they're very similar. They're similar in shape, different in size, depending on the kind of width of the floor at that particular point. So you can think of the area of the cross section as a function of the position that you are along the floor. And as we get to the very end, we can see that the cross sections get smaller and smaller in size. Now, why might you want to find the volume of such a structure? Well, for heating and cooling purposes, it would be absolutely essential. So the most important thing here is we are going to be relying on a formula for the volume of such a solid, which we derived in a video called Volume the Calculus Way. And you can see that basically the integral sign sums up, is basically a sum of an infinite sum of all the areas of the cross section. So if you could imagine not just the limited number of cross sections I've shown here, but adding in every single possible cross section, that is what the volume formula, how it emerges. It's just the infinite sum of all those cross sections. So if that formula looks unfamiliar, you might want to check out that video, and I will link it in the description. But without further ado, let's get started. So let's look at creating these 3D structures with some common cross sections that you will come across, and we will begin with making them perpendicular to the x-axis. Later we'll look at perpendicular to the y-axis, but this is a little simpler of a treatment. So there's our volume formula. And as you can see, we're going to begin to situate things in the Cartesian plane in order to be able to use our calculus formulas. So right here we have the x-axis, the y-axis, and what you are looking at right here, so let me just use maybe light purple, this region is going to be the base of our building from which we are going to erect perpendicular cross sections. So right now you can't see those cross sections because they're coming right out at you. We have just an aerial view of the base of our building. So now to help us along, let's consider square cross sections to begin with. We're going to tilt this a little bit on the side here just to make it easier to look at. So this is the y-axis, this is the x-axis. And we're going to envision building squares off of this. So what might those squares look like? So trying to get sort of a three-dimensional effect here. They are going to be looking somewhat like this. I know that looks like a parallelogram, but it's supposed to be a square with perspective. And as you can see, they are perpendicular to the x-axis. So a square back there is going to be a much smaller square, but if we take another x value and look at the square across here, it's going to be much bigger because the height has to match the base, and the base is bigger right there. And finally, sort of more towards this end, we'll get a smaller square again. So the question is, we know that the formula for the area of a square is just going to be the side squared, whatever the side is. Now, what is the side? Well, let's look a little closely here. The length of the side is going to be this distance here. But what is that distance? Well, if we come back to the curve over here, just to maybe erase the inside for a minute just to help us, we realize that that distance is actually the vertical distance between the two curves. So we can actually find that distance. And if we, let's see, for simplicity, if we call this top function y top, we're going to put yt for y top. It could also be f of x. And let's call the bottom function y bottom, and that could be g of x. But I'm going to be using yt and yb often for obvious reasons. It makes it a little easier to remember. So that vertical distance is just going to be, so this distance here is just going to be yt minus yb for any particular x value. So we are going to have yt minus yb. Now we're not going to calculate that for a specific x value. We're going to keep that as the general formula because we want this to be able to work for whatever x value we choose. It's always going to be the y coordinate of the top function minus the y coordinate of the bottom function. So that's our general formula for square. And if you prefer to use f and g, you could also, you have to remember which one's on the top and which is on the bottom. You could also write the formula like that. Another common cross section is rectangles with height h. H can be fixed or h could be a function of x. So let's say that it was they were rectangles that were fixed, maybe 1 unit high. So the height would not change, but definitely the length of the rectangle will change. And clearly what everything hinges on is the base times height. Once again, this is the base. The base is just yt minus yb. And then the height is h. So we would get the base is yt minus yb, and we would just multiply by whatever h is, whether it's a constant or a function of x. So now let's take a look at semicircles, another common cross section. So here's our figure again, and our semicircles taken perpendicular to the x-axis once again. So perpendicular. Our semicircles would look like this. Pretty small one there, and as the distance between the curves or functions gets wider, our semicircles will get bigger in area and smaller once again. So for a semicircle, we know that the area is going to be 1/2 pi times the radius squared. To get the radius, it might be good to think about what the diameter is. And the diameter, once again, the diameter is just that distance yt minus yb. So if that's the diameter, then the radius will just be 1/2 of that. So over 2, and our formula becomes 1/2 pi the radius squared. So the distance between, the vertical distance between the curves or functions squared. And another common one, a little trickier in terms of the formula, is equilateral triangles. So equilateral triangles will be looking like this. Take one a little further along, it's going to be much bigger. And a little one here. And so you can kind of envision the figure, the three-dimensional solid being created. And for the area of a cross-section of an equilateral triangle, we have to look at an equilateral triangle a little more carefully if you don't recall the formula. So that the base of the equilateral triangle we know is just going to be yt minus yb again. And for an equilateral triangle, if we recall 60, 60, 60, but we'll make that 60, 30, 90 therefore. So this distance will be 1/2 of yt minus yb. And then if you recall that to get the height, you just have to take radical 3 times the short leg, which is yt minus yb over 2. So our area formula becomes 1/2 the base. Well, when I say the base, I mean the whole base. So yt minus yb times the height, which is rad 3 times yt minus yb over 2. And just to tidy this up and make it a little easier to remember, I'm going to bring this 2 inside here. So we realize that we have yt minus yb over 2 squared with just a root 3 in front. So if we look a little closely, the formulas are pretty similar for semicircles and equilateral triangles. It's just this kind of constant in front that's different. So with all that prep work, we can get into the fun stuff now. So for our first practice problem, we're going to consider the region bounded by these 2 functions, these two graphs, and we are going to construct this solid by building square cross sections perpendicular to the x-axis. So this is a wonderful visual created by this gentleman in GeoGebra. I love this. I had to borrow this because I couldn't hope to do it justice. So here you see the beginnings of the cross section. So this is f of x equals the square root of x, and here we have g of x equals x squared. And you can see the cross sections beginning to emerge, the solid beginning to show the three-dimensional object, but we are going to find the volume of the solid, but here is the solid. It's kind of beautiful. So if you fill in all those square cross sections, you see the actual shape of the three-dimensional solid. And you can kind of see the like along here, you can kind of see the edges, the one corner of the square, and here, here the other corner of the square. It's a pretty cool shape. Now we'll get into the mechanics of finding the volume of the solid whose base is this shaded region and whose cross sections are squares perpendicular to the x-axis. Now, because we are looking at an aerial view, it's going to be obviously impossible to sort of show what it looks like exactly, the figure, but hopefully you remember that from before. But what we do need to understand is that we are dealing with squares, and what the base of the square is spans the width of this region. And I'm going to do is, instead of the squares, imagine that square is like coming right out at you. I'm going to kind of fold those squares down to the side, because this is a useful technique to be able to think about the area of a cross section. So that might be the square at that particular location x, whereas further along here, say here, where that distance between the curves, the vertical distance is much smaller, the square is going to be much smaller. Now, what were the curves again? In case you forgot, the top one was the square root of x, the bottom one was x squared, and it could be sort of easily shown that they intersect at the point 1, 1. So let's go to the formula for the volume of any solid. It's the definite integral of the area of the cross section from a to b, the limits of integration. So here's our formula for the area of a square cross section. So we remember, what is yt minus yb? It is this distance from here to here for any particular x value. So let's get into it then. So the y top is rad x, and y bottom is x squared. So we're not putting in a particular value of y. Remember, we're putting in the general equation for y given a value of x. Now, if we're going to put this into the volume formula, we need to expand this, which is to multiply this by itself. So if we did expand that, and we got rad x times rad x, we would get x. And if we multiplied the outer and inner terms, we would get 2 rad x times x squared plus x to the 4th. And that would be if we FOILed that out. And for simplicity, it's probably good to rewrite this as this is x to the half times x squared. So x to the half times x squared is x to the 5/2. So now we can just dive straight into the volume formula. So we are going to take the volume from, so what are a and b? Well, a is the lower x value, the lowest limit of where they intersect, so that's 0. And b will be the x value at which they intersect again, which is 1. So it's the integral from 0 to 1, and it's of x minus 2x to the 5/2 plus x to the 4th dx. So we're going to do this one by hand, and in later slides we're going to just use the calculator to work these out, but it's important to see one worked out by hand first. So the antiderivative of x is half x squared. The antiderivative of x to the 5/2, let's see, we add 1 to the exponent, so that would be x to the 7/2, and then we would divide through by that 7/2. Here, the reverse power rule, and I guess it might be easier just to multiply by the reciprocal, and if we do that, at this point, it would come out to 4/7. And then this would be plus 1/5 x to the 5th. So the definite integral, that's the antiderivative, and then we just have to plug in the upper and lower limits. And luckily 0 would just render 0, so we only have to plug in 1. We'd have a half minus 4/7 plus 1/5, which simplifies to 9/70, which as a volume, as a decimal, is approximately 1.1286 so that should be approximately for future reference. So that would be the volume, and whatever the units of measurement are, it would obviously be units cubed. That would be the volume of the solid that we just saw in the previous slide, created by cross-sectional squares perpendicular to the x-axis. So for our second practice problem, we are actually going to take the same region as for the first one, and this time we're going to build a solid by using equilateral triangles perpendicular to the x-axis. So again, from this website by Michael Andrzejkovic, I'm not sure if I'm pronouncing it correctly, he created this on GeoGebra. There you see the triangular cross sections. And when we add them, sort of put them all in, fill in from the beginning to the end, we see a beautiful three-dimensional solid again. And this time, you notice it just has one spine that's kind of spanning on either side, but that's the general shape of the figure that we will be finding the volume of. So here we go, looking at it two-dimensionally. Here's the problem. So here's the region, and the triangles, the equilateral triangles are coming out at us. Sort of very hard to see unless you do this. So here's the base of an equilateral triangle. If we fold it to the side, it would look something like this. And similarly, a little further along, if we fold that down to the side, we have this shape. Why that's helpful is we realize that everything hinges on this distance, yt minus yb. The top y value minus the bottom. And once again, we do need the equations of the top function and the bottom function. And now let's pull up the formula for the area of a cross section when it's an equilateral triangle. If you recall, you had to take the vertical distance yt minus yb and have it, square it, and then multiply it by rad 3. So we covered this in an earlier slide. So if we just put in these values now, so yt is rad x minus x squared over 2 squared. Now, we're going to be doing this using a calculator, so it's kind of nice to tidy it up a little bit before we put it into the volume formula. So generally, what I like to do is kind of break it up as rad x minus x squared, the numerator squared over 2 squared. So you can just square the top and bottom separate. And we realize that that 2 squared is going to be a 4, and we can pull that out of the integral sign. So we have that rad 3, that's a constant. We'll pull it out of the integral sign. And 2 squared is 4. We can pull that out. And then we just have the integral from 0 to 1 of rad x minus x squared squared. And we know that if we had to do this by hand, we'd have to FOIL that out, as we did in the case before. But fortunately, if we use the TI graphing calculator, and if you go to the math menu and choose 9, which is fn int, you will be able to pull up, well, first of all, type in rad 3 over 4 first, then choose math 9, and it brings up the definite integral formula. And just when you enter it, be sure to be careful with parentheses. You've got to make sure these parentheses are kind of standard, so anything else that has to happen within that has to get a separate pair of parentheses, like this case in wanting to square this quantity. And the answer comes out to be 0.0557 rounded units cubed. So you can see that this is fractionally a smaller solid than would have been created than we did see when we had square cross sections. So for our third practice problem, We'll switch up the region a little bit and we'll use semicircular cross sections. Once again, perpendicular to the x-axis. I know I keep saying that, but it is an important distinction, and we'll do a couple of cases where it's perpendicular to the y-axis shortly. So here is the region, and we are going to be creating semicircular cross sections. So flattening those down to the right just to get a better visual feel for their shape. There we go, their shape and size. Put a few representative ones there. And if we recall, the formula for the area of a semicircle is half pi r squared. So this quantity here is obviously r. So what's yt and yb? Well, yt must be, the top function is the linear one, so that's x plus 1. And the bottom is e to the x over 3, therefore. And clearly, yt minus yb is this distance, the vertical distance, which would be the diameter of the semicircle, and that's why we have to take half of it. So if we just continue to work things out here, we can put in yt as x plus 1 minus e to the x over 3. That's all over 2 squared. And because we'll be using the graphing calculator, it's good to get out any constants that you can. So I'm going to take this 2, square it, make it 1/4, bring it out, combine it with the half, and we get pi over 8. And we're left with x plus 1 minus e to the x over 3 squared. And we know from the volume formula that we just have to take the area of the cross section, pop an integral in front of it, and go from a to b. So in fact, I'm just going to do that right now. I'm going to say the volume is the integral with respect to x of that cross-sectional area, and I can keep the pi over 8. I can bring that out as a constant. And a is the x-coordinate, the lower bound 0, and b is 5.7, so from 0 to 5.7. Now you're given that, but if you weren't given that and you had to find it, you would type in y1 equals x plus 1 into your graphing calculator, y2 equals e to the x over 3, and then you could find out where they intersect to get that value of 5.7. And using the graphing calculator at this point, the volume, would come out to be 1.98 cubic units. So for the fourth practice problem, we're going to use the same region, but we are now finally going to deal with cross sections that are perpendicular to the y-axis. So semicircular again. So what does this mean? Now, the first time we're doing it across perpendicular to the y-axis. So what you're going to say, imagine we were looking at y equals 2. Keep that constant. The cross section there would be like this. So the orientation would be slightly different. So we would have it, it actually looks a little, the perspective looks a little better when we draw it perpendicular to the y-axis. It looks a little more realistic. So this is what we mean by perpendicular. The base of the cross section is perpendicular to the y-axis. And so if we, any typical cross section would have to look like this. Oops, not very accurate, but here we go. And this one up here would be a lot smaller. So this changes things up a little, because if we now think about what the diameter of any one of those cross sections are, to find the diameter, we'd actually have to take the x-coordinate of this side. Let's call that the right-hand function, xr. And we'd have to subtract out the x-coordinate of the function on the left. So the diameter would be this, which means the radius would be half of that. Kind of looks very similar to the formula from before, except that now we are dealing with x's instead of y. So this is what the formula for the area of the cross section would be like. Notice that the area is going to be a function of y. And let's show you how that happens now, because to find xr, we actually have to do a little work here. We have to take the formula and xl. We have to take the formula, say y equals x plus 1, and solve that for x. So if we subtract 1 from both sides, we get y minus 1 equals x. And that is the formula for the left-hand function, y minus 1. So that's x expressed in terms of y, and we have to do the same for the other function. So to deal with e, we're going to take the ln of both sides. So we get ln of y equals x over 3, and then cross multiply by the 3, and now we have both functions expressed in terms of y. So why is that important? Well, now we can plug that into our formula. So xr equals 3 ln y, and xl, now you're going to have to put this in parentheses just because of all these negatives, is y minus 1 all over 2 squared. So now we do see that that is indeed a function of y. I'm going to bring the 2 squared out again, so make this pi over 8. And now I have 3 ln y, and I think I'll distribute that negative just so I have less parentheses to enter into the graphing calculator. And to get the volume, I'm going to integrate this with respect to, notice, be careful here, now it's with respect to y, which means that I actually have to use the bounds in the y direction. So the lowest y bound is 1 at the bottom where they intersect, and the upper one is 6.7, so it would be from 1 to 6.7 this time. And if we use the graphing calculator, we would get the volume to be this. It's actually very similar to the one before, not exactly identical, but close in volume, so 1.98 units cubed again. And for our last practice problem, we were going to repeat practice 4, but this time with cross-sections that are isosceles right triangles, with one leg in the region and perpendicular to the y-axis again. So we didn't actually treat this situation before, but it's really important to be able to deal with any figure that they kind of throw at you, say on the AP exam. So isosceles right triangles, so that's why it's so important to be able to sketch the cross-section. So the leg of the isosceles right triangle has to be perpendicular to the y-axis and in the region. So we know that it's going to look like this. This side is congruent to this, and that is a hypotenuse. So something like this. And we know that this distance is going to be xr minus xl, as we discovered before. And so this distance will be xr minus xl. So this is going to help get us the formula for the area of the cross-section. So here's the volume formula again. This time I've written it in terms of y, and I just use c and d as opposed to a and b to indicate that you have to be aware that the y limits, the upper and lower limit, change if you're doing it with respect to y. And here is the formula for the area of that cross-section. It's half base times height. So in fact, it's actually just half of the formula for what the square is. So if we flip that over, the area of the square we know from before is xr minus xl squared, and we want half of that. So we are going to have half of the xr is 3 ln y minus y minus 1 makes this. And then we know that we're going to find the volume. We just are going to, let's see, keep that half out, take that out of the integral, and we're going to go from 1 to 6.7 again, because this was with respect to y. And here we do this on the graphing calculator, the TI-84. Notice that instead of y, I've just used x. And that's because x is the most obvious variable to use on the calculator. It's the most readily accessible. So as long as every y, you just use x in place of that, it still is doing the same exact calculation. I could call that variable z, and it wouldn't matter. It would be the same calculation either way. So our volume for this in this scenario with isosceles right triangle cross sections is approximately 2.52 cubic units. And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.